I'm going to talk about my research in what I love doing, which is studying the universe. The universe as an evolving thing with an origin. And I do my work at the South Pole. I do my research at the South Pole. And so this is our telescope, which I'm very proud about. We'll talk more about that toward the end of the talk. But I just want to warn you, don't call it a satellite dish. I'll get a little touchy about that. It's a very precise, very accurate millimeter wavelength telescope, 10 meters at the South Pole. One test, and this is the first big test that it passed, that if inflation is right, remember I gave you that example with the paper being crumpled up. If inflation is right, then if we try to measure space-time, the geometry of space-time, it should be Euclidean. Light rays should be that. Space-time should be very, the jargon we use is flat. Not flat like, a pancake, but that light ray should curve, right? Or inflation should lead to a flat universe. So how can we check that? Well, imagine you're at the South Pole. We like to put the South Pole on the top. And you want to measure the Earth. Is the Earth flat? You're going to ask that question. So you take your graduate students and you say, go 300 miles out, take a left turn, make a perfect right angle, go 400 miles, and then just come home and measure all the angles, right? And, So right away you know there's something fishy going on, because there's a right angle, here's a right angle, and yet you meet. So the sum of the angles add up to more than 180. You probably remember that's bad. Or if you like Pythagorean's theorem, 3 squared, 4 squared, that's not 5, that's 4 again. Right? So you say, oh, don't worry, the Earth's not flat. And you use this information and you calculate the radius of the Earth. But then, you go to bed. When you're in bed, inflation strikes. And I don't mean mild inflation. And it expands, and it expands, and it expands, and it expands by the number of times the universe has expanded. You wake up the next morning, you think, I'm not sure we did the measurements right, and you send your students out, and they get, it's perfect. It's perfect. You send them as far as they go. They could be traveling for the 14 billion years and measure the triangle, and it's flat. And as far, the age of the universe, like as far as you could see, it's flat. Right? It's very hard to have a theory like inflation say it's going to be sort of curved. It's driven flat. So we want to measure, is the universe flat? Right? And this is what supposedly inflation did to the universe. Now before I tell you how we do that, let me just say, if you like what inflation says, and I think this is very cool. It says that when you look at this map, this image of the baby picture of our universe, and you see these slightly more intense and less intense, hotter and colder spots, what you're seeing is subatomic quantum mechanical fuzz that has been stretched out to the largest structures in the universe. So you say, what does quantum mechanics look like? That's what it looks like. It's just an amazing thought. So I'm going to show you some pictures which are from an undergraduate textbook on how you can measure. Of course, it's a pretty new textbook, but how can you actually check this? And the answer is in the cosmic microwave background, but not in that map I showed you. That map I showed you is 7 degrees resolution. That's almost as big as your hand, the spots on the sky. And at the time, when you see the cosmic microwave background, at that almost 14 billion years ago, that angular scale is much bigger than light could have traveled at that time. We call that super horizon, bigger than the horizon. So you can't see structure growing because you're not looking in the right scales. You've got to get higher resolution. But if you could have higher resolution, then you can do this experiment. You could say, well, what are the structures that could grow that within the horizon? What do they look like? And if they look like, and you can actually calculate from first principle how big they are, in kilometers, or whatever, your farlongs, whatever unit you'd like. And then how do they look? Well, if they look real big, it's because maybe they're this big, but light that you see is bending, right? So they look bigger, right? And this is what would be called a closed universe. The geometry would be closed. If it's just Euclidean, or what we would call flat geometry in the mathematical term, you can calculate what they'll look like. And if they're open, or this kind of funny saddle universe, will look like this. So we and a couple of other groups set out to do this at that time. This is not this is the first telescope I worked at the South Pole called DAISY, sitting there. It fulfills the promise of all telescopes looking weird, but you can't tell if half the people are bald, all our hats on. We went to the South Pole, and you say, well, why the South Pole, right? Well, one is, we're looking at microwaves. How do you heat up your cup of water? If you're going to make tea, you put it in a microwave oven, right? The water and water vapor, it reacts and absorbs water very, very strongly. So we want to look at microwaves. We want to look for this very little water in the atmosphere. Turns out the South Pole is the driest desert on Earth, or the middle of Antarctica. Not necessarily the South Pole, but the South Pole is very good. It's very stable. The sun goes behind, and the atmosphere gets very, very stable. So it's very, very good. It's actually quite high. The pressure altitude is usually around 11,000 feet. And that's because this ice and snow you see is 2 miles thick, right? There's a continent under there. It's not like the North Pole. And so you're up high. That helps you above all that. And so in the same textbook, Freeman, the universe, they say, okay, which one is right? So this is the closed or the Euclidean. Inflation says it better be this, or you got a terrible theory. Inflation's a terrible theory, or this. And it wasn't DAISY. I was hoping it'd be DAISY, but it's Boomerang, and it's this one. You can, by eye, see that. Now, I'm going to show you in a little bit that we don't just hold up maps by eye and do our theory that way, but you can see that that's the case. The universe is, in fact, as best we can tell, the geometry of the universe is flat or Euclidean.